Okay, my friends, this is going to be fun. I just got tipped off to this particular video from my friend Erico up in Canada. And he says, is this atomic vapor, is this light that's being given off? Now, this goes back 6 years ago, so this is not brand new, but I don't know if anybody has understood what this triboluminescence in slow motion really consists of. At first, I thought it was the breaking of bonds, and then I realized, no, it's not. Okay, my friends, this requires no geekness whatsoever to understand this. This is Alex Smith. This goes back 10 years ago, and he's got a classroom full of kids, and he's showing them how H2O is a product of H2O2 after you explode it. And when you hear the explosion, it's gonna blow your eardrums out. Now, here's what happens. H and O is hydrogen and oxygen. Okay, they're both gases. They just float around in the air, but hydrogen is very explosive. And now why? And there's no physicist can explain this. No chemist, no physicist. H is the smallest particle of atom that exists. It's just supposedly one big positive core and one tiny little electron. Why, if you add a spark to this, would it create so much of a gigantic explosion, which you will see happen? There is no explanation for it, and the reason is they don't realize it, but these hydrogens are made up of 1,823 electron dipoles. Okay, they're dipole electrons, and when you add an extra electron or two into here with a flame or a spark, the whole thing blows up, and then you get all these particles going, and what a bomb it is. And what the product will be is vapor, water vapor in the air. It'll have H2O instead of H2O2. So we lose an oxygen in this explosion. So every H2O2 turns into a H2O, and the water molecules will be in the air. And the other oxygen turns into electrons. Basically, that's what happens. That's why it's so explosive. And an oxygen has 16 particles like this size, and every one of them is 1,823. So when it goes off, 16 times of 1,823 open up in the air and make this explosion. That's why it's just so devastating. And if it was just one big solid core, it couldn't possibly happen. So listen to the explosion. Here he goes, and the kids are going to go freaking wild. Now listen to this here, and again, it's Alex Smith. He seems like a nice guy. I would like to have him for a professor.
Because then the pressure in your mouth.
They think it's funny. You see all the oxygen? That's all water. That's not smoke. That's water. This is why you should turn kids on. You see this? This is exciting. This is what should happen every day in class, everywhere. Look, he's having a blast.
So this has to do with reaction kinetics.
All right. This is really what the proton exists of. Is all these black particles in the center. We never realized it. We always thought it was just one big proton in the center and one tiny little electron. No, it's the proton is coated by a ton of electrons, and it's the same, I believe, number of electrons as there is of the dark particles, which are the muons. And they are surrounding the black particles. And this is what a photon looks like. It's the smallest stable particle there is a photon of light, because you have two dipoles back to back. A single electron, a single dipole electron is not stable. It will want to fuse into something. It's like electricity. It'll want to burn into something. It'll want to penetrate something as heat. This bounces off because it's got a field completely surrounding it. This wants to attract into another field to become, a partner of something. And this is what they become stable at a certain number. And I can't really, I've been racking my brain trying to figure this out, but there's some kind of vibrational influence that causes at certain periods, which are the periodic table, and it appears to, they sort of stay stabilize at these quantities. Another one of those, boop, and it sort of gets stabilized. Another one, boop, it sort of gets stabilized, more or less. But in between, there is thousands of particles in between each one of these stable units. All right, so hydrogen is not just one big heavy proton. It's 1,823 little tiny particles. Helium is not 4 little particles, which is 2 protons, 2 neutrons. It is, I think it's 7,350 electrons, something like that. Everything is made up of just bigger, more balls of electrons. And that's electron flood theory. I can account for everything with the 100%. If you can come up with any single thing that is unexplained, I think I can explain it. I'll try. Bring it up to me, because I'm showing things that nobody else can explain. They can't explain gravity. They can't explain black hole, the dark matter, none of that stuff. They can't explain anything because it can't be explained with the standard model. It does not work. Okay, my friends, check this out. Very cool. These are some kind of mints. And he's going to smash this with a big heavy-duty hammer, and it creates spark, lightning almost looking like, and shifted to the blue. Now watch. Boom. You see the blue sparks? Now at first when I was watching, I'm thinking it's discharging. You see how it discharged to the anvil-looking thing underneath it? Watch. See how it's discharging down at the bottom, like looking for, I thought it was looking for ground. So I'm looking at it, I'm thinking, well, I can understand where if you had excess electrons, they're going to try to drive themselves down into the ground. That's how ground works. It absorbs electrons, and anytime you see a glow, that means you're seeing electrons. All right, so I'm thinking I'm sort of understanding it, and then this happened. All right, remember I said I was at first saw it and I could see discharges going down into the anvil that he has sitting on when he smashed it, and I thought it was seeking ground. And I saw ones like this that just showed radiating. I'm thinking it's breaking bonds, and when it breaks the bonds, you get the electric discharge. Well, not so. This is a 22 caliber pellet gun shooting into this. He smashed it with a hammer. This is a gun shooting into it. Now, just before it hit it, watch what it did. This is what freaked me out and explains everything. All right, there's the pellet. Didn't hit it yet. Why is it glowing blue? Didn't hit it. What do you think? Why would that glow blue like that before the pellet even hit it? I think I understand. I think I know why. And I think I could show you the same reaction happens on our moon. I know, this is crazy. This is crazy stuff. But I get so many things from so many different people. And as I keep looking through them, nothing makes sense at first. And then all of a sudden, everything makes sense. What it's doing is it's crushing the atmosphere. Literally the atmosphere that surrounds this lifesaver. There's an atmosphere surrounding, and this is called Casimir effect, when you push field against field. This has fields on it too, and it probably has something that has excess electrons because it's reactive. You know, I would say it's probably got something that has a little extra energy in there, which coats this with electrons basically. And when this pushes against those electrons with its electrons, they start to glow because they're being forced. These electrons are being forced into this material and it's making it glow. So there's no fracture, there's no bonds breaking. It's just excess of electrons being pushed in here. And when he smashed it with the hammer and so forth, same thing happens. You force a whole batch of electrons down into it, and they have to discharge somewhere. This is forcing the air right in front of it to discharge into it. And the same thing happened on our moon. You see this? This is just outrageous. All of the light research, basically, that I show was the experiments were done by Rod Warren. And this is his nephew, Dylan Carpenter. And he just sent me these, and I haven't had any contact with him since. But he said, well, what do you think? And I sent him back, and I said, yikes. And at first I had to really do some thinking. But I can tell you what's going on here. The moon is going this way. It's not spinning. The moon doesn't spin. Planets spin, but the moon doesn't. And the moon is going this way, and it's literally crushing the air that, whatever the atmosphere is here around the moon. It's going to be an atmosphere, and it's crushing it as it pushes itself into the particles that are coming at it. Because all of the moon just absorbs particles. They come in and they hit it. So it's coming in and it's pushing back against it, which creates the blue shift. This is a blue shift. Red shift is where you pull the particles away from each other, and it shifts into a longer spectrum. This is forcing them together, crunching the waves to be real close, which makes it glow in the blue. I hope to make this understandable. Everything there is made of these two particles. Everything. And 1,823 of these two particles together make up a proton, and not just one big proton. Let me just show you what they look like. All right, here's a representation. Let me back this up a little bit. All right, here's the representation. Right now they say that's a proton. And if you smash it to bits with these gigantic super colliders, you can break this into quarks and this and that. And the smallest particles they've ever found are these two. So they smash this to bits, dig through all this stuff for years, and they find these are the smallest things that exist. They keep finding them, but they are the smallest particles. We started with light. We did not start with this. All right, what is this actually made of? It's made of this. All right, this is actually what a proton is. It's 1,823 of these dipoles. And a dipole means two poles, a positive and a negative. And the two of them together like bar magnets, and they glue to another one. And it becomes a stable photon. One of these is not stable. And when they break, these two can break apart, and they're not stable at all. This is one of these here and one of these here. You would call those electrons. Nobody knew about the black part before. The only reason we know about it is because we can see it made from light. And we can actually divide these particles from each other, and the black goes on its own way, and the white turns into a shower, and here it is right here. All right, the black just can't get through the Venturi. And that's the design of the Venturi. And again, this is Rod Warren, not me. He discovered this by accident, and he was just showing pictures. I don't think I know he didn't know what he had going on there. And when I saw it, I said, whoa. And he worked with me for 6-7 years. And I haven't heard from him lately, so I don't know. He's just not interested anymore, it appears. But this is his work. I want to make sure that's fully understood. So let's just go through it. There's just light coming through, having a nice time, the normal. Then it's accelerating because of the Venturi, and at the Venturi it explodes, and the white part separates from the black, which is fission, and that's fusion. When they break apart, that's what it is. Fission breaks, fusion comes back together. Now, I never knew this could happen, but they separate, and the black particles in space will congeal in the center, and all the white particles surrounding it. That's what black holes are. That's a black hole in space. It was done by the Russians in 2014. They didn't know what they did either. They had no idea this was going to happen. They expected it was going to come out with almost like stripes in a lattice work in here, and every particle would push every other particle apart because they don't want to be next to each other. The white ones hate each other. The black ones, they couldn't care less. They would just pile up right in the center. They're fine. And the white ones crushed around them, forcing them into the center. And white being attracted to the black is electricity. That's what electricity is. And if you can separate that white out and then let it go through a wire to get to the black, you can use all the electricity you want. And guess what? I think we can do that. You see this? Once again, Rod Warren just accidentally did this. He was going to do a double slit experiment, but instead he made a single slit with two nails, literally nails, very small nails, and he put them right next to each other to make a slit. So you got a nail going down here and a nail going down here, and he just shined a laser into it, and when he did, the curve of the nails forced all of the fields, and they're big. You see the size of the fields? They had to crush down into that venturi, which accelerated the hell out of the light. Once you put a big volume into a small volume, the only thing that can happen is either it accelerates or it just splatters everywhere. Well, we made it accelerate, well, Rod did, through this little tiny slit. And I worked with him for, like I say, 5-6 years. It had to be. And I asked him, try this, try this, try this. He did all kinds of things. He must have put in, I can't imagine, a number of hours. And I don't have the ability to do this. Somebody the other day said, well, why don't you just do it? I can't do it. I don't have the time. I tried, trust me. And my stuff just was nothing. His stuff is absolutely fabulous. So, again, somebody can do this. He's not the only one that can do this, but he's just the first one that did it. And without this, I couldn't prove my electron flood theory. Now, what can we get out of this? Can we get free energy? I say yes. That white is the only thing you want to put in a battery. And to rip the white away from the black is a lot of work. It's a lot of work, except here, it is no work at all. It forces itself not to let the black through. It says only you white guys can come through. Come on, come on, come on. All the black balls stay out. They are fixed particles. They cannot squish down, as I have shown you right here. That's what Fermilab says, fixed and point. These can go squishy. This can never changes. And here it is right here. I agree with the 100% fact. That's the black ball. Never changes. Same with this one. This one can get big and it can get small. And it gets big when it pushes against other particles. All right, and then we had fission and fusion. I mean, this is serious, serious stuff. And we should be using this to get free energy. And I really see no reason that it wouldn't work. But anyway, getting back to these experiments and so forth, I showed you the blue being crushed by this moon forcing itself in. See all these fields? All particles are going through those fields, and every time they move through a field, they get slower and slower and slower and slower. And eventually they become so slow that they call it the cosmic microwave radiation background, which means particles that are just sort of drifting around. And then other particles that are have acceleration to them banged in and out of them and causes what they call a quantum foam, little particles flickering on and off all the time. And the other ones that are coming fast through them start to slow down. Bing, 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 bing. And that's just it. Now they're not going anywhere anymore. And space is not a vacuum. I mean, it's absolutely saturated with particles. You look at some of these pictures from the Webb telescope and Hubble and all that. There's nothing but a saturated. It's like a soup. Particles of light don't go the same speed through that soup. You see that? That's another one Dylan sent me. I think this is Jupiter. It looks like to me it has two magnetic fields, and it has some kind of strange dipole effect going on here. Normally you would see just a nice white and a nice black, like all these over here. These are just normal dipoles. This is spinning in reverse and traveling forward through the solar system, instead of moving along the correct way, where it sort of rolls along its course, rolling like a tire along a road in a circle. The tire's going backwards. So it's scraping like hell. And it seems to make two fields. You see this? This is a field right in there, same field. And this big field there's a real strong field, and there's a weak, gigantic field. And Venus spins backwards, and it's going to have a hell of a big magnetic footprint, because it's particles, instead of sort of rolling like I say, a tire down the road. It's going down the road, but it's going backwards down the road. And it's just like it would rub the tires off of your car. It's rubbing all the electrons, causing huge magnetic fields. That's what Venus is. It's a backwards planet. And you see these two, there's two separate looking fields to me. I don't know how you see it, but I see it as two completely separate fields caused by two separate magnetic interactions, where the whole thing is moving through the system like this, which everybody else is too. but everybody else is spinning in the correct direction so that they don't overload. This one came out backwards, and it's scrubbing instead of sort of rolling. It's scrubbing backwards. If that it makes sense to you, I hope it does. So don't forget, I have to come up with a solution to every single thing I see, or electron flood theory doesn't work. I don't go with this, well, that's something we can't explain, but we know everything else. No, if you can't explain that, you don't know anything. You have to know everything, or you can't explain anything. Now, this I looked at long ago, and this is, I believe they call it sonoluminescence, or whatever it is. They put a firecracker down inside this tank of water. They blast it off, and they're going to look at, I think, 120,000 frames per second. It goes like this, and then when it comes back together, the coming back together is more explosive than the exploding out. Why would that be? Okay, my friends, this is way beyond cool. This is going to be an implosion. Well, it's an explosion implosion. They're going to take inside of a water tank a firecracker, and they're going to put it in there, and it's going to explode. And they're going to take this at 120,000 frames per second. And you see exactly what's going on. And now with the electron flood theory, I need to explain what's going on. And I don't think too many people can. And I'm seeing things in there with this very, very fast frame rate that I can see a lot of detail that was before never seen. Now, this goes back 7 years ago, and I remember watching this a long time ago, and yeah, I sort of thought I had ideas, but now I think I really can't remember what I ended up with, but I do know this is very, very interesting. So get ready, here goes. This is a slow motion, guys, slow-mo, guys.
A little funk. Smells good. Ready?
Now watch.
Whoa.
Now watch it come back. Look. Did you see that? When it came back, it was more explosive than when it went off. Here they go.
A little funk. Smells good. Ready?
You know what? I'm going to put this down to an extremely slow speed. All right, so they're in 100 and whatever it was, 1,000 frames a second. Now we just upped that 4 times. So let's go back here. Here we go.
Smells good.
Here we go. Let me take the words off. It does take a little longer. There it goes. Pow. Now, look at the expansion. All right, so what is expanding? What's expanding there? There's gases created in the explosion, and anytime you create gases, it means you have broken apart something that was solid and you're just making it bigger. And this is what's happening to the Earth right now. Every time we burn stuff, it gets bigger and bigger. So anyway, it went off, it's expanding. Now after it expands, it's going to crush itself back together. Now let's go with it. Here goes. All right, get ready. Now it's going out. Now I'm going to want you to look at some of the surface characteristics too. It went way out. Well, there's another shot that shows it better. And it comes back. Now look at the glow. And look at what you got here. You can almost see through here and here. Like that's just still water. This appears to be the gases and the air. All right, now let's see as it comes back together, tighter and tighter. Look at the glow. I'm turning it on and off as it's coming back. Look at the glow more and more. Look at that glow now. Look at that. Why is it glowing so much? Why doesn't it just collapse? Look at that. Now it's just solid white glowing like crazy. Look at the rays coming out of it. It's getting hotter and hotter and hotter. That's got to be very, very hot. Look at that. Looks like the sun. And boom, it's out. And then all the gases go into the water. All right, here's a different shot. Look, boom, it comes out. Now watch, there's going to be colors and stuff. Watch around the edges. Let me turn this off. Might be a little better. You're going to see like little flickering lights and so forth. Now, and you'll see a lot up here at the top too. But you see the little glowies and little different colors? Let me come back for a second so you can see that again before it starts to collapse. All right, it's expanding. Look at what's going on in there. All right, this is the burning stuff. You can understand that. Now look at these little tiny particles around it, the different colors. And you're going to see that there's a lot up at the top now. I'm sort of up in the air about that. But there's different colors, the red, the blue, the greens. And now it's collapsing, and then it'll just go off like an atomic bomb. Pow. All right, they're shooting with 2 different frame rates. So you can see inside and outside, basically. All right, 2 different exposure rates to show information in different areas. So inside and outside, basically. I'm going to get ready to stop it because we got some very interesting stuff shows up here. No, I just stopped it. Now I'm not exactly, I gotta be honest with you, sure what the frame rate changes, but it appears that this, I don't know whether one's slower than the other. Obviously one's slower than the other. I should look into this, but it doesn't mean that much to me. I'm looking at the inside effect, and this is apparently the outside effect. All right, now watch what's going on inside here. Really dynamic system going on in there. See all the colors? Watch them up here. See all the colors? Isn't that cool? Look all around here. Look at all these little bumpy looking spots on there. Those are electrons pushing other electrons away. Look at that. Look at that. Look at all that stuff going on there. Look at those colors. See it up to the top? Now that's got something to do with the cord that they were hanging in there when the thing went off. It's got something to do, there's more reactivity up there. Probably due to some of the particles or whatever, because that's what's up here, is these particles. Right here. You see the different colors? Those are different energy levels of, you know, they always appear to be like blue, green, and red. Isn't that amazing? See them all over here popping. And now it's going to start to crush itself. The water's coming in. Look up here to the details. That's up here. It's got something to do with the disruption of this little cord. And now it's glowing like unbelievable. imminent collapse. Now, at the very end, what happens to all that glowy stuff? Boom, it's gone. What happened to it? Now, that's deep inside. This is on the outside. It's still glowing. And poof, out it goes. Total elapsed time is 0.01 seconds. All right, now they're going to show how, first of all, you got that hole in the water. What happened to the rest of the water? It just went poof like this. Poof. Well, watch the surface, what happens. Because you have to move that water out of the way somehow. So get ready. Pow, it goes off. Sooner or later. Later than sooner, but it will go off. Boom, there it goes. Now, see it all lit up under there? So far, nothing's happened. Although there is some strange characteristics going on there. Let's go back just a sketch here. Hold on. All right. It's just laying here sort of flat. It's going to take a couple of seconds. But I did see some... This stuff, why is that doing there? I don't see any light yet. There's no light. How did that happen? Why is this like that? I can see bubbles and everything. And this is still going on right now. Boom, there it goes. And now it starts to rise above that area. But we saw all that stuff before this. Before the flash of the light. That's kind of interesting. Now everything's shooting out of there because it's just being compressed upwards. Look at all the colors. You see all the colors? Isn't that cool? And that's the shock wave straight up. So that's where it gets its ability to cavitate. And it creates that little cavity in there. And then when everything comes back down, it crushes the light particles that were in there, or the gases, or whatever it is. I'm not sure exactly what it is, but it just glows like crazy and then just snuffs itself out. So I don't really know. But look at this. Coming straight up. Now what does really intrigue me though was what happened before. You know, I would like to know when they actually, we might, oh, you know what it is? I know what it is. Let me come back to here. All right, hold on. Now, you see this stuff here? They lit the thing and dropped it in there. So there's going to be some kind of stuff going on. These little bubbles are coming up. That's all that is. And then it goes off. Watch. Those are bubbles from the fuse that lit it. And it's burning underwater. And those are little bubbles that are coming up in the vapor. You see it? See the vapor and all these little things? And now it just went off. So that accounts for that stuff being ahead of the explosion. Okay, I give it a little more consideration here, and here's what I came up with. This is the underwater firecracker explosion. This is what happens. This is what the explosion is you have your dark core always in the center, and you have your layers of electrons coating it. Around the whole thing, you got water, all the way around the whole thing. All right, and here it is here exploding. Now, what happens? Most of the electrons have push to shove. They have the field, so they're trying to explode out, but they're being pushed back. The black is totally different. The black is not being pushed back. The black is just going straight out. So up above, we're going to see water trails coming straight up through the top, just little tiny straight up trails. And I say those are the result of the black particles being pushed so hard that they're going bam, 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 bam. They're pushing all the other ones straight out through here. Now they're pushing them out here too, but they can't get very far because they're in a solid block of water basically. Up here it can rise up a little bit, and it does. Now again, this is where the gases from the burning wick are showing up here. So we haven't got an explosion yet. Very shortly we're going to get the explosion and see those spikes coming straight up. Now here goes. Just keep an eye on it. All right, so it's going to come up to start popping sooner or later. Here we go. Now you see the whole surface is rising just a little bit, so it's already exploded down here. We can see a little tiny taste of explosion. Now look at this. These straight up lines. Why are they straight up like that? Why wouldn't the whole thing just go, whoops. Let me get back to here. All right, why wouldn't the whole thing just come up? You see you got some little lights and stuff going on here. Little colored particles are coming up. Most of the colored particles are staying down. The black is shooting these streams straight up. You see that? Just stop for a second and look, think about what you're seeing. What we got is these straight up trails. And as far as I'm concerned, that is these right here, the explosions shooting these black particles out, because they can get past the water. They really don't have that field around them, so they can move faster in this medium than the reactive white particles can. Water is extremely dense. Do you know that water cannot be compressed? You can't compress water. There's so many molecules, so many atoms, electrons in water. You cannot crush it. It's just, my father told me that when I was a little kid. He says, you know, you can't crush water. I said, what are you kidding about? You jump in water and it just goes away. He says, yeah, it'll move out of the way, but you can't crush it. You can't put it in a can and force that can to crush. It won't crush. It's just too many electrons packed in too small of a space. Hydrogen and oxygen is H2O, all right? You hear me? Hydrogen and oxygen. Wait till I show you what happens when you put hydrogen and oxygen in a balloon. This is going to blow your mind and probably your eardrums too. But this is what I'm saying is happening here, is the dark particles, not the white ones. The white ones, a few of them are escaping here and there, but not like the black ones. The black ones can go through. They don't have that field to push back against them. Out they come. The white ones are being pushed down, and that's why they collect in that ball in the center. All right, so this is just about at the point that all of the particles have escaped. Basically, they're gone. Now the whole thing comes up with it. This is after the explosion, and pops the water up in the air. But these trails here are the giveaway that those are tiny little particles shooting up through that water, which is not compressible, so it's got to get out of the way. And what it does is it pushes it or drags it or pushes it ahead of it, one or the other. But they're coming up in these little straight, more or less, lines. Okay, I'm going to sort of wrap it up for today, but the next thing I'm going to do is go through the Crookes radiometer, because I have to explain every single interaction. This is still a mystery after 150 years. Nobody knows how it works. Now, this guy came up with a new theory about it, and nobody's listening to him because that's what happens. But this guy explains it very well, and he shows what the guy did was he took all new lasers and so forth. Instead of having just radiation coming out, he pinpointed it in certain ways to show the effect it would have on the Crookes radiometer. And the Crookes radiometer just is a thing that spins around when you shine light on it. I'm going to show this in very great detail because I think I might have an idea. But there's things that nobody's taken into account. There's a dome that goes around. Glass, you can go right through glass, yes, but it does restrict some of the UVA and UVB. There's a difference in the frequencies that come through, but anyway. On the inside of the glass is going to be a layer of electrons. On the outside of the glass is going to be a layer of electrons. I don't think anybody's ever taken that into account. So that's one thing. And then I got some other things to go about it. And, you know, how the things, and you know, how they're pushing against it and so forth, the white and the black. And anyway, we're going to go through all of that. I got a pretty good long thing going on, but listen to what he has to say about this Crookes radiometer experiment. And this is very nicely done. That's a Crookes radiometer right there. You put it in sunlight, and it starts to spin. And it spins only one certain direction. But if you put it in a cold, it spins the other direction. Why? And anyway, there's a lot of details to go through on that. So, but let me just finish it up with this. Here he goes.
Paper positing that this repulsive force is also responsible for Brownian motion, which is the movement of fine particles suspended in water, and also the phase transition of materials from solid to liquid to gas. He theorizes that this jump in electron orbitals provides the initial kick to move atoms and molecules away from each other and start a phase change. Now, time will tell whether this new theory will stand up to further scrutiny and experimentation and be accepted by the scientific community. I actually haven't found any papers replicating Lou's experiments or commenting on his methodology, but it just goes to show how much more there is to the simple radiometer than meets the eye. 150 years later, and we're still not quite sure how it actually works. Anyway, that's all I have for you today.
All right, he did a nice presentation. It's our own devices, and it's called the Crookes radiometer, a surprisingly persistent scientific mystery. And it is a mystery. Nobody knows how it works. And I'll tell you, it's perplexing. But there's things that nobody's taken into account. There's a certain amount of gas you have to have in there. You can't have a perfect vacuum, but you can't have just a normal amount of gas either. It's got to be a diminished amount of gas, almost a vacuum. And then there's a bunch of little details about it. But anyway, that's the next video. All right, I love you all. And it's time to take a whole new look at science. Whole new look, really, because the dipole electron flood theory, it literally changes 100% of everything about almost everything. If you don't know how you're starting with what you're starting with, how do you know what you're ending up with? You know, chemistry works pretty good. They've got that stuff down pretty well. But when you get down into the subatomic realm, they're just clueless. All right, anyway, love you all. Talk to you later. Thanks. Bye. My friends, this just came out a few minutes ago. Riding the cosmic wave, how plasma instability is changing our view of the universe. What I show is plasma. The white particles I show is plasma. And I've talked about the effect of the outer atmosphere scrubbing the particles in space, because space is not a vacuum. And when it does, it creates the instability in the plasma in this cosmic area. And that's what they're talking about. They're catching up. You see this? This is plasma. Plasma means disassociated particles, and the black has disassociated from the white. Normally these two were attached together. We created from the muon and electron neutrino, which is a pair. We separated them and sent the muon on its own way, called a sterile muon, and the electron turned into showers. This is supposed to be billions of electron volts, and this is plasma, and this is changing the way we see the universe. It's literally changing the way they see the universe is now that they're understanding the plasma a little bit. You see this? Now that they know about the plasma a little more, that you can separate the white from the black, it's changing the view of the universe. This just came out today. And they're trying to look into the cosmic events that create the plasma. Well, the plasma is creating, it's called ionization, and it's being created where there are ionosphere, ions, a lot of extra electrons, is spinning with the particles in space and scrubbing it, creating a very, very cosmic plasma out there at a certain layer at the edge of the ionosphere where we scrape through the rest of the universe. And that's what's causing global warming. We got a lot of thinking to do. Everything has been totally misunderstood at this point, as far as I'm concerned. I could be totally wrong, but without having an engagement of a discussion about this, we're just going to continue rolling down the road in reverse. It's been 60 years. They still don't know how gravity works. I mean, it's absolutely incredible how they've missed everything because of Einstein's theory that nothing can change with the speed of light. That has destroyed everything, destroyed all the research in space. all of the research basically into particle physics in the subatomic realm. In the atomic realm, yes, once you get up into the atomic realm, that stuff works pretty good. But there's a lot to learn about that too, because there's a lot more particles that they never realized were there, all these isotopes. They know they're there. They just skim over the top of them. And those are the things that allow life to literally work, it's isotopes. So we got a lot of talking to do. Anyway, that's it for now. But this plasma I'm showing you is changing the world, the universe, how we look at it. It doesn't work the same. We thought all light comes just never slows down. No, they realize now that's not true. And all of that stuff is part of this plasma. So I love you all. Talk later. Bye.